Okay. We learned about all of the reactions that we need for this chapter already. Really, the last thing we have to do is put everything together and talk about synthesis. So synthesis is just the process of making one molecule from another. It can happen in one step, it can happen in multiple steps. You can be tasked with synthesizing a molecule from one specific starting material, or you can be asked to synthesize a molecule from anything that's commercially available from one of the big chemical companies or something like that. But let's start with just a simple one step synthesis, which really isn't going to feel much more different from what we've already been doing. So for this sort of thing, we're either going to have a substitution, an elimination, or an addition. Those are the only kinds of reactions we've talked about so far. So substitution, that was chapter 7. Elimination, also chapter 7. And then addition is the stuff that we just talked about. The exception being ozonolysis, which is kind of its own weird thing, but it goes in with chapter 8. So if we're given a problem to solve, like this, how do we go about doing that? And there's a 3-step process that you can remember, although you'll probably end up doing this just sort of by instinct at some point. First, we want to look at what changes have happened molecule. Look at what changes have happened in the molecule. Specifically, look at functional groups. Okay, so in this example, right, we're going from an alkene to an alcohol. Okay, that's the only real thing that's changed. Next, we want to figure out what type of reaction that is. Okay, so going from an alkene to an alcohol, what kind of reaction is that? Hydration. Yeah, hydration. And at this point, if you have a reaction type where Markovnikov versus anti-Markovnikov is of importance, this is a good point to look for that. So do we need to be concerned about Markovnikov versus anti-Markovnikov with hydration? Yeah, so we've got 2 potential positions on this alkene where we could put the alcohol. Okay, one of them is Markovnikov, and the other is anti-Markovnikov. Okay, so we have the Markovnikov product. And so we should note that not only are we doing a hydration, we're doing a Markovnikov hydration. All right, and then all we have to do is select our reagents. Okay, and this is where you're going to need that sort of pinwheel chart. Have I been calling it the pinwheel in here? I've been calling it the pinwheel in Bluffton. Do we know what I'm talking about? The cheat sheet on Blackboard that's got the center, the alkene in the middle, and all the different reactions. I call it the pinwheel. All we need to do now is take our identification of the reaction as a Markovnikov hydration and translate that into the reagents that we actually use. So we've actually got three options for Markovnikov hydration reagents. We can use H3O plus, or very similar to that, water and sulfuric acid. Okay, those two things mean the same thing. Or we can do oxymercuration. Okay, specifically with Markovnikov hydration, we have sort of these two categories here. For these, there is a possible carbocation rearrangement, but for oxymercuration, we're not going to get a carbocation rearrangement. So, based on the reaction going from the starting medium to the products, well, we make a carbocation. Do we have to worry about it rearranging? In this case, we don't, because when we form the carbocation in the first step, okay, we break that bond, put the hydrogen here on the less substituted carbon, and the positive charge goes on the more substituted carbon. So that's now a tertiary carbocation, which is happy and it's not going to rearrange. All right. So we don't go back, please. We don't specifically have to avoid carbocation rearrangements. So we'll go for one of these options. And so what you would actually write for your answer is something like that. One thing I should mention is that you do not, for these kind of problems, need to draw the mechanism unless I specifically say design a synthesis and draw the mechanism of every single step, which that would be a lot to do for one question. So these are just basically what reagent do you need to turn one thing into another. Okay, and then sometimes you might have like this, a case where it's going to be like a two-step reagent, but you know that oxymercuration, the oxymercuration conditions are sort of one package that goes together. So we still call that one step. Okay, where things get more interesting is when multiple steps are required to get from the starting material to the product. I'm going to show this through two different examples of multi-step synthesis themes that show up fairly often. The first is changing the position of a halogen or an alcohol. Okay, so if you see a problem, you're asked to do a synthesis and you see that a halogen or an OH group has moved. You don't know a way to do that in one step. Okay, and so we'll have to do multiple steps. How do we do that? For this particular example, changing the position of a halogen or an OH, we need to do an elimination reaction. Then we need to do an addition reaction. Okay, so elimination and addition are pretty much opposites of each other. But if we can control the reagents that we pick for the elimination and or the addition, we can move one of these groups around the molecule. Okay, so let's say that I ask this. And say, okay, come up with a synthesis for that product starting from the starting material. Okay, so we can't do this in one step. If you go through all the reactions that we've learned, there isn't one that just magically scoots the bromine over. And so for multi-step synthesis, by definition, we're going to have intermediate molecules in our synthesis. So, right, this question mark is actually sort of multiple reaction arrows. And so one way we could write that out is saying, all right, so we'll have our starting material, and then we'll go to some intermediate that we don't really know the identity of yet, and then that will turn into our product. Okay, and maybe in the middle, instead of one intermediate, there's two or three or four. Keeps going on and on. Okay, specifically for this sort of type of multi-step synthesis problem where we're moving a halogen, and actually for the other example that I'll show you too, the intermediate is an alkene. We are talking about alkenes in this chapter after all. All right, and so actually what we should do here is go back to these steps and make sure that we're doing all of them, fully. Okay, so identify the changes in the molecule or the functional groups. Okay, so clearly our only functional group here is the bromine. Okay, the bromine is moving from the blue carbon to the green carbon. Sorry, I have green and not pink today, but that works. Okay. So that means that our intermediate alkene needs to be an alkene where there's a double bond between the blue carbon and the green carbon. Okay. So our alkene is going to be that. Reason is when we do, okay, so the first step is elimination. All right, that matches up. We take an alkyl halide, do an elimination, we get an alkene. Elimination, then addition. Okay, so second step is addition. And yes, that makes sense. We go from an alkene to an alkyl halide. And we can also see that, yeah, when we do an elimination on this first alkyl halide, right, we have the option, is the double bond going to go to the left or the right? Okay, it's gone to the right here, so we'll have to make sure that we select a reagent that will do that. And then going from the alkene, doing the addition reaction, going from the alkene to the alkyl halide, now we've got to pick, okay, are we going to put the halogen on this carbon of the alkene or on this carbon of the alkene? Okay, and again, we're going to have to select the reagents correctly so that we get the right selectivity. So for the first reaction, this is chapter 7 material, okay? So it's going to be an E, it doesn't really matter if it's E1 or E2. But it's an elimination reaction. And so in order to do that, we need a strong base, okay? And if you look on your chart from last chapter, one of the common ones is sodium methoxide. Okay, this is not a bulky base. Okay, and so that means that our double bond is going to go to the right, where it's more substituted, rather than to the left, which is less substituted. If you wanted to go in that other direction, you would need a bulky base, which is potassium terbutoxide. Okay, another thing I would do at this point is ignore the second step and just look at the first step. Look at your chart and say, okay, is this reasonable? And this is entirely last exam material. And once you're satisfied with that, all right, so now we're good. Now we know we've made this alkene intermediate. And now to make things easier again for us, we're going to ignore all of the first step. Okay, because we did that, we know it's right. Okay. And this is something that I recommend you do really for any synthesis is don't try and look at the entire process. I mean, sometimes that's good, but it really is a sequence of individual steps. Okay. All right, addition reaction of this alkene to make this alkyl bromide. So we have Markovnikov or anti-Markovnikov addition. Which one? Yeah, this is Markovnikov because it's going onto the green carbon, which is a more substituted carbon. Okay, and for actually, so we're putting the cart in front of the horse here. So I've said it's an addition reaction. What kind of addition reaction is it? We really need to be more specific than that. Is it a halogenation? It's a hydrohalogenation. Okay, so now you can look at your pinwheel chart and look for hydrohalogenation reagents. So it's Markovnikov. And so the reagents for a Markovnikov hydrohalogenation are just the acid corresponding to your halogen. Okay, don't write HCl. That doesn't make any sense. You know what for the ad? So for hydrohalogenation, we just use so we use HX, where X is the halogen. Yeah. How did I come up with that to begin with? It's from it's kind of memorization, honestly. Yep. Well, the the two atoms that are being added across the double bond in this case are literally the reagent atoms, which is the case half the time, maybe. The other half of the time, it's not quite as easy, but.
Thank you. I think the obvious.
Well, I knew, yeah, after the fact looks obvious, but before the fact, it's like, ah. So now I can erase our this thing. Okay, so now there's our synthesis, right? And so let's see. The things I don't you don't need to write, don't need that, don't need that, don't need this, don't need it. You just need the reagents and the intermediates. So this is sort of the full written out version that includes the intermediate. We can also write an abbreviated version that doesn't include the intermediate and shows the two steps on the same reaction arrow with different numbers. So first step, sodium methoxide. Second step, HBr. Gives us the product. So another thing that is not directly related to synthesis, but is a good thing to bring up here is sometimes I might give you a question that looks like this, right? This looks just like a predict the products question. However, if you go on your pinwheel chart and you say, uh-oh, there's no reagent that's sodium methoxide and then HBr. That's not, we didn't learn about that combination. And the reason is because it's a two-step thing. Okay, so if you see some reagents that are in sequence that aren't a pair of reagents that always go in sequence, then you'll need to sort of in your brain split everything up. No, that is not what I wanted to do. Split everything up into individual steps and figure out, okay, what's that intermediate? Do the first step just by itself and then do the second step just by itself. Okay, and that's how you get to the product for something like this. Okay, unless I specifically tell you, it's okay to write this abbreviated version that doesn't show the intermediates. However, fairly often I will ask you for the intermediates, so be aware of that. Okay, for changing the position of a halogen or an alcohol, we did elimination and then we did addition. Okay, the intermediate was an alkene. So instead of changing the position of an atom, let's change the position of a pi bond. So this is going to be the opposite of what we just did. Okay, so we're going to do, in this case, addition first. Then elimination. Okay, and the intermediate is going to be, well, a halogen, I should say, an alkyl halide. Or an alcohol. Okay, so the what we're moving around, the pi bond, that's backwards. Addition and elimination, that's backwards, and then the intermediate is backwards. Okay, so that could look maybe like this. All right, we're moving the pi bond from, well, from one place to another. And in the last step, we used the blue and green carbons to denote the two positions where interesting things were happening. Okay, and those ended up being the two carbons that made up the alkene in the intermediate. We're going to do something similar here in that we need a carbon atom that's common between the two alkenes. Okay, and it's that carbon right there. Okay, in the same way that our colored carbons above ended up being where the intermediate alkene was, the blue carbon here is going to tell us where the alkyl halide intermediate is going to be. All right, so now we can split this up into two reactions. Where our intermediate is an alkyl halide or an alcohol, but we'll use an alkyl halide on the blue carbon. So we have addition as the first step, elimination as the second step. Yep, that's an addition reaction, and that's an elimination reaction. So we'll take the first reaction just by itself. What type of addition reaction is this? This is also a hydrohalogenation.
So where would the hydrogen be? Would it be next to the BR? Technically, it's a oh no.
It's right there. Because when you do an addition reaction, any type of addition reaction to a double bond, you're going to add something to one carbon and something to the other carbon. Okay, in this case, the hydrogen is not usually drawn, but if you're going to draw a hydrogen on that intermediate, that's probably the one you should draw because it's the one added in that reaction. And then is this Markovnikov or anti-Markovnikov? Yeah, this is anti-Markovnikov. What reagents do we need for an anti-Markovnikov? Hydrohalogen. So we do need HBr, but we need something else to make it anti-Markovnikov. Yep, peroxide. Okay, so now we'll look at the elimination reaction. We're eliminating so we have two options when we do an elimination. We can go left or right. Right goes to the more substituted carbon. Left goes to the less substituted carbon. Okay, so our elimination is making a less substituted alkene. And so we can't just use any old base. We have to use a bulky base, okay, for the less substituted alkene. And our bulky base of choice is potassium butoxide.
Wait, so how do you get KO plus B again?
So potassium butoxide is
Yeah.
this guy. So the potassium is K, O there, and then this is tert-butyl. So another way to write potassium butoxide is TBUOK. Is that what you're asking?
No.
Oh.
Specific sports types you're using, or it can just be any of the alcohols or not.
This one is specific. You want to use potassium butoxide specifically.
How do you know use potassium?
Yeah. So because we want the less substituted alkene, usually if we do an elimination reaction with like sodium hydroxide or sodium methoxide, that's going to eliminate to make the more substituted alkene, which would be there. But in order to, so we've got two protons that can be deprotonated in that case, those two. The bulky base, potassium butoxide, will selectively deprotonate this less sterically hindered proton. Right, and so we can write this for our abbreviated synthesis. So for these, the HBr and peroxide, where both of those reagents are used at the same time, you can use a slash, you can use a comma, you can use a plus sign, anything except an additional number, right? Because if you wrote this, that's wrong, okay? Because the HBr and the peroxide have to be have to go together. React flask at the same time.
The combined form we could put, like for the single phase one, when we did the H3O plus, we usually do H3O plus, or we could do H2O and.
You can literally write or. Yeah, that's legal. Okay, let me pause this for just a sec. We're gonna go to the problem set. I just want to make sure I erase the ones we did, because I think the ones we did are really good. Sorry, in Bluffton, I don't want to spoil anything. Hello, Zoom, please. Sorry, I have to see my face. Okay, there we go. All right. So here is, go away, please. Here's the homework. Okay. I think most of you guys have already started on this, but first question is just asking Markovnikov versus anti. Second question is um, asking for predicting the products. Now, many of these look like they are multi-step, but I think, yep, all of these are actually single-step synthesis reactions. In all of these particular cases, the 1 and 2 are steps that go together as sort of as one unit. 3 is mechanisms, so there's a small selection of mechanisms that we talked about. Maybe it didn't seem small, but relative to all of the different reactions we talked about, there's some of those. And then 4 is sort of the big one, and that is to design a synthesis for some various reactions. Now, some of these will be of the type that I just demonstrated, the moving a position of an alkyl halide or moving the position of a pi bond, but others like C, the chlorine just disappears, okay? And the methyl group is now the other direction. So that seems a bit strange. It's not going to fall nicely into one of those two categories, and but the reactions to get to that point are reactions that you know. Let's see. Let's see what else. Some of these may be single step, some of these may be multi-step. And then at the end, there are these word problems. So I'm not going to ask stuff like this on the exam. But this is kind of the way that a lot of times chemistry is written out in the chemical literature, not as puzzle questions like this, but in many cases, right, chemists write stuff out in words, especially old papers where typesetting the chemical figure, the structures was a giant pain. And so this is just sort of a different way to think about it. For all of these, you should be able to pretty much go directly to a skeletal structure. And then once you add all of the sort of puzzle pieces from the text, it should be a little more clear what it's asking you to do. So again, just treat those like anything else, doing it step by step. Any requests on here?
With their skeleton structures?
Like associated with these?
Yeah.
No, you have to come up with them. So like for 7, the first thing you'd need to do is draw a skeletal structure of this, so you can see it better. Yeah, let's not do those. Those are just for the nerds who do this for fun. Okay, one should be easy. You should be able to do that. That's funny. That was literally the one I was about to do. Okay, so let's do H. All right. The first thing, before you even look at the starting material, well, maybe that's not a great piece of advice for later, but in this chapter where we're just starting with alkenes, the first thing you need to do is look at the reagents, okay, and figure out if just like what kind of reaction are we doing today, okay? We can't do a substitution. We don't have an alkyl halide. We can't do an elimination. We don't have an alkyl halide or an alcohol or anything to eliminate. Sorry, in the starting materials. Yeah, so we can't do an addition or we can't do a substitution or elimination reaction on our starting material. The only thing that we can do that we know how to do is addition. All right. And so even at this point, even if you don't know what the heck HGOAC does, you can draw the skeletal structure or the the core of the molecule. Oh, that looks like a wedge now. Sorry. And say, all right, it's an addition reaction, and so we're going to end up with two things that have been added to the carbons that were part of the double bond originally. Question is, what are those? And for that, you're just going to have to look or memorize your chart. The mercury acetate and sodium borohydride, what's that? So this does a hydration, specifically a Markovnikov hydration, and it does not allow for a carbocation rearrangement. So the Markovnikov product is going to have the OH of the new alcohol on the more substituted carbon. So right there. Okay, and the hydrogen goes on the less substituted carbon. So that's our product for this one. In this particular case, if we used a different hydration, a Markovnikov hydration reagent like H3O+, in that case, there would be the potential for a carbocation rearrangement, but the carbocation that you would form would be tertiary, right? Because this alcohol product is tertiary, okay? And so there's actually no reason to use mercury here.
Mercury on these for 2 degree, right?
Yeah, generally speaking, in order to prevent rearrangements. Let's do.
You do want Wilkinson's?
Wilkinson's, yes. Where was it? Here it is. All right, Wilkinson's catalyst. So, H2 is the reagent. So what kind of reaction is that? Yeah, ignore the Wilkinson part. What does H2 do? Yeah, addition, specifically hydrogenation. Okay, so we know our product is going to be, gimme. It's not erasing. Thank you. I did it again. Okay, whatever. So our product is going to be this, all right? However, there's a difference between H2 with Wilkinson's catalyst and H2 with palladium or platinum metal, okay? The palladium or platinum metal does syn addition, and Wilkinson's catalyst does anti-addition, all right? So this is not really an adequate answer. What we need is something that shows that the two hydrogens are anti to each other, as opposed to what we would get if we used palladium and H2 and palladium or platinum, which is both of the hydrogens on the same side, whether it be both on wedges or both on dashes, doesn't matter. Okay, and again, doesn't matter for this one, for the first answer, whether the top one's on a wedge and the bottom one's on a dash or the other way around. We're just showing the relative stereochemistry for that one.
But if it was uneven, you would have to do like and if it wasn't like a two methyls attached, if it was like a methyl and a methyl.
Yeah, I'm not gonna require you to do that though. But yes.
Mhm.
Let's do one of these ones where we remove the alcohol. Okay. So if we're changing the position of a halogen or an OH, we need to do elimination and then addition. All right. So that means we're going to eliminate, and so this so the carbons that are, sorry, I didn't use color. Let me do that. Okay, so the OH starts on the blue carbon and ends on the green carbon. And so that means our alkene intermediate has the double bond in between those two. Okay, let's actually do the second step first, because the second step is a bit more straightforward. So this is a hydration reaction. And is it Markovnikov or anti-Markovnikov? Yep. So reagents for an anti-Markovnikov hydration are BH3THF and then peroxide and sodium hydroxide. All right. So that's the second half. The first half, though, is a bit more complicated. Because we have to make the OH into a good leaving group. Okay, in order to do that, we actually need another intermediate, and that is the tosylate. Remember that one? Okay, and then we can go to the alkene, and then do BH3THF. So let's fill this in. Okay, to convert an alcohol to a tosylate, we need tosyl chloride. And then to do an elimination, here we don't have to worry about the more or less substituted alkene because they're going to be the same either way. Okay, and so we can just use really any strong base. So let's do sodium hydroxide, I guess. Okay, so this is one valid answer to the question. Or we can do the abbreviated version, in which case, first step, tosyl chloride, second step, sodium hydroxide. Doesn't really matter where the arrow ends up going. Third step, BH3THF, and then 4 is this. So here we're taking right this last step with the BH3THF, hydrogen peroxide, sodium hydroxide. 1 and 2 now get bumped down to 3 and 4 because they're later in the synthesis. So this is sort of a 3-step thing that's shown in 4 steps because one of the reagents is like a double step kind of thing. So if I do not ask you to draw intermediates, then this is an acceptable answer. All right. So take a stab at the homework that will be due next time. Also, I would recommend, I know there's a lot of problems in here, so I would recommend leaving at least some of them for right before the exam. There's also a ton of practice for this stuff online. Just look up addition reactions of alkenes, and there's bazillions of this stuff. All right, see you Wednesday.